748 gigabytes of coherent memory in a desk-side AI machine sounds absurd, but that headline number can either unlock enormous models or create enormously expensive patience. NVIDIA's personal AI lineup now spans two very different ideas: compact DGX Spark for desktop development and DGX Station for workstation-scale models and sustained professional workloads. Spark uses the GB10 Grace Blackwell Superchip, a 20-core ARM processor, and 128 gigabytes of unified system memory shared across its integrated CPU and GPU. Station jumps to the GB300 Grace Blackwell Ultra Desktop Superchip, 748 gigabytes of coherent memory, and NVIDIA's claimed peak of up to 20 petaflops. So this is not merely one product in two sizes. Spark emphasizes accessible experimentation. Station targets massive local inference, fine-tuning, and long-running agent workloads. Traditional GPU systems divide fast video memory from ordinary system memory. Large models hit that wall quickly, even when the computer has plenty of RAM elsewhere. Unified or coherent memory gives processors access to a much larger shared pool. That can reduce awkward model splitting and let previously impossible workloads load locally. Here is the catch. Fitting a model and running it quickly are different achievements. Memory bandwidth, compute precision, kernels, and software support still control the experience. Spark's 128 gigabytes are unusually roomy, but unified capacity should not be mistaken for 128 gigabytes of top-tier discrete GPU memory running at identical bandwidth. Both systems lean heavily on Blackwell's low-precision AI capabilities. FP4 can increase throughput and shrink memory demands, provided the model, runtime, and quality target cooperate. Spark's 1,000 trillion operations per second and Station's 20 petaflops are headline peaks tied to specific low-precision conditions, not universal application speedometers. A model's parameter count does not translate directly into one fixed memory requirement. Precision, quantization metadata, architecture, context cache, and runtime overhead all change the total. At 4 bits, 1 trillion raw parameters alone suggest roughly 500 gigabytes before overhead. That explains why 748 gigabytes is meaningful, not magically unlimited. NVIDIA says Spark supports models up to 200 billion parameters, while Station targets models up to 1 trillion. Treat those as supported workload classes, not guaranteed speeds. Long prompts and growing conversations build a key value cache that consumes additional memory. Agents running many steps can therefore squeeze capacity even after model weights fit. Spark looks most compelling when a model exceeds ordinary consumer VRAM. Yet the workflow still values a compact, integrated development box more than maximum token throughput. Think prototyping, evaluating larger quantized models, building retrieval pipelines, testing local agents, and preparing software that can later move onto bigger NVIDIA infrastructure. Spark CPU is ARM64, not the x86 architecture common in desktop workstations. Containers and Python may travel smoothly, but native dependencies still deserve verification. A supported CUDA path, optimized inference engine, and correct quantization format can matter more than impressive silicon specifications. Unsupported operators turn hardware ambition into debugging sessions. Spark includes 4 terabytes of NVMe storage, useful for keeping models nearby. But storage capacity does not substitute for active memory once inference begins. NVIDIA says a dual Spark configuration can support models up to 405 billion parameters. That expands the workload, but communication between boxes becomes another performance variable. Splitting a model across systems requires moving data across the link. More total memory helps capacity, while synchronization can limit how efficiently added hardware becomes speed. Station's 748 gigabyte coherent pool attacks that problem differently. Keep an enormous workload inside one tightly integrated workstation, rather than coordinating several smaller desktop devices. The obvious users are AI labs, research teams, advanced developers, and organizations evaluating frontier-scale open models without sending every experiment to shared cloud infrastructure. NVIDIA specifically positions Station for long-running agents. Large memory can hold substantial models and context locally, while dedicated workstation resources avoid competing cloud queues. Keeping development local can improve iteration, data control, and availability. It can also make costs more predictable when a team repeatedly runs heavy workloads. Hardware location alone does not guarantee privacy. Telemetry, remote tools, model downloads, application design, and network configuration still determine where sensitive information travels. Both products are promoted for fine-tuning, but the method matters enormously. Parameter-efficient tuning is far lighter than updating every weight with optimizer states and gradients. Loading a trillion-parameter quantized model for inference does not mean training that model from scratch. Training demands vastly more memory, computation, data, and time. Aggressive quantization saves memory and can unlock larger models, but quality impact varies. A smaller model at higher precision may beat a larger compressed model for your task. Do not judge these machines with one peak number. Measure time to first token, generation speed, concurrent users, context size, power draw, and output quality. Station's real decision includes acquisition price, power, cooling, support, and utilization. A spectacular machine sitting idle can lose economically to cloud compute, rented only when needed. Spark should be compared against existing GPU desktops, high memory Macs, rented accelerators, and remote servers. Its advantage depends on your models, software, patience, and budget. Choose Spark when compact size, 128GB capacity, NVIDIA's AI stack, and local development matter more than the fastest possible response from conventional discrete GPUs. Choose Station when enormous models are genuinely central to the work, jobs run frequently, local control matters, and the organization can support workstation-scale infrastructure. Choose neither when smaller models already solve the problem, workloads are occasional, required software is unsupported, or cloud flexibility beats owning specialized hardware. The important trend is bigger shared memory beside capable AI compute. That combination makes local model development less about squeezing into VRAM and more about choosing trade-offs. DGX Spark makes huge memory local development compact. DGX Station makes frontier-scale experiments physically local. Neither makes bandwidth, optimization, compatibility, or economics optional, and that is the reality check.